Let's continue to discuss the next project, machine learning for pions. This is an energy regression problem to develop machine learning algorithm for pion energy estimate. First, let's introduce the concept of hadronic shower. In the standard model, there are two types of the hadrons. First is meson, second is baryon. Meson is composed of quark and antiquark, while baryon is composed of 3 quarks or 3 antiquarks. The famous example of meson is pion. In the pion family, there are pi plus, pi 0, and pi minus. Pi plus is composed of UD bar, pi 0 is composed of UU bar or DD bar. Pi minus is composed of down quark and anti-U quark. The famous example for baryon is proton. Proton is composed of UUD. The other famous example of baryon is neutron, which is composed of U quark and 2 down quark. When hadron interact with the materials, it will initiate hadronic shower. This is a cartoon to show how hadronic shower is developed. A neutron enters into a material, play the role as absorber, which will absorb energy of the incoming neutron. The concept of interaction length means the mean free path for neutron interaction with the material. The interaction here is a strong coupling between the neutron and nucleus of the materials. It will initiate a lot of hadrons. For example, you will initiate a lot of pions. The incoming neutron might still have a substantial energy, and it will be diffracted into scattered directions. Pi 0 decays to 2 photons, close to 100%. When photons interact with materials, it will convert to E plus E minus pair production. The energetic electron interact with nucleus can initiate brainstorm radiation of the photon. This type of the cascade initiation particle production process is called electromagnetic shower. This is the EM component of a hadronic shower. On the other hand, through the quantum chromodynamics, an energetic quark can radiate a gluon, and this gluon can split into quark-antiquark pair. As you can imagine, there will be a flux of hadrons initiated from the incoming hadrons. These hadrons are primarily composed of pions, and with a strange quark content, you can also have kaons. These pions, with the sufficient energy, will continue to initiate strong interaction with the nucleus. Therefore, there is a hadronic energy component of the hadronic showers. In order to measure the complete energy of the incoming hadrons, we have to measure both the EM component and hadronic component of hadronic showers. To do so, we have to design a combination of the sub-detector system in order to measure different components of the particles. This relates to different radiation particle interactions property with materials. In this cartoon, you see a cross-section of a quadrant of the Atlas detector in the Large Hadron Collider. Starting from the collision point, there is a pixel detector, strip detector, and transition radiation tracker. This detector can measure the trajectory of charged particles. Right behind that, there is an EM calorimeter and hadronic calorimeter that can measure the EM shower and hadronic shower of the radiation particles. Behind, there is a muon spectrometer. Most of the radiation particle, their energy will be absorbed before reaching out muon spectrometer. Only the muon will reach the muon spectrometer. Through the combination of measurement, we can identify different types of radiation particles. For example, protons leave charged particle trajectory in the tracker and penetrate through the EM calorimeter, eventually deposit most of energy in the hadronic calorimeter. With that brief introduction, let's move on to the topic of the pion energy regressions. As commented earlier, there are different components of the sub-detector system in order to measure radiation particle in the Large Hadron Collider. When the pion initiates from the collision point, it can deposit charged particle trajectory in the pixel SCT and TRT detectors, and then eventually it will reach out EM calorimeter and hadronic calorimeter. The EM calorimeter and hadronic calorimeter usually participate into different detector cells. The electronics can measure the signature deposit in each of the cell. The cell usually represent in eta phi directions. Phi is the azimuthal angle with respect to the beamline direction, while eta is the polar angle with respect to the beamline direction. In order to measure the longitudinal profile of a hadronic shower, the calorimeter is also divided into different layers. Here is a 3D model of a ATLAS calorimeter. Pay attention on the human being scale. This is the largest detector in the world. Let's focus on the calorimeter. They are EM calorimeter. This is the liquid argon technology, shown as a copper color here. Outside is surrounded by the tile calorimeter, which is designed for the hadronic shower detection. Let's focus on the EM calorimeter. There are barrel part, which is transverse to the collision point. In front and back of the barrel, there are two end cap calorimeters. They can measure particle in collision flying to the forward regions. The EM calorimeter is composed of pre-shaper, front layer, middle layer, and back layer. Each layer have a different granularity in eta phi. The eta phi granularity of each layer is different. Combine all information, we are allowed to efficiently reconstruct different types of the hadronic shower and separate them from the EM photon. Through combination of information from different detectors, we are able to resolve single photon from two photons and eventually categorize the different type of the incoming particles. For hadronic calorimeter, there are also barrel part and end cap part. This is a table to summarize different absorbable material for the EM calorimeter and hadronic calorimeter, and the active material to measure the ionizing energy coming from the showered particles. The eta represent different angular coverage of each of the subsystems, and there's a huge number of radar channels to cover the full range of the detector. It's both detectors, they are working close to 100%. They are very efficient detector. The goal of using this data set is to do the energy regression. The reconstructed energy is coming from the machine learning estimate. We can take the ratio to the truth energy. If we have a very good energy regression model, the ratio should be close to 1. We can categorize the performance of our energy regression model as a function of the truth energy of the pion. The dataset you are going to explore contains the energy eta phi of each detector cell. The hadronic shower has been clustered. You are encouraged to study more details in this document that can inspire you to develop the model to carry out for the final project. Next, let's talk about the charge particle tracking. This is actually the same data set we have used to learn the graph data structure. In the future high luminosity LHC, each collisions will contain high number of the bunch crossing. It results to a huge number of the particle produced per event. Therefore, it's necessary to develop an efficient algorithm to do the particle tracking, to resolve all these orange tracks for each of the collisions. In the right side, this is the cross-section view of the detector. This detector is composed of a pixel detector and strip detector. And strip detector is categorized as an inner detector and outer detector. In the forward regions, there's also an end cap detector and this detector. Our task is to connect the raw hits into the trajectory. Once we have a trajectory, we can use that to estimate the track parameter and convert into the full momentum of the charged particles. The task due is an edge classification problem. With the graph data, each of the hits can be denoted as a node. We want to connect the edge between layers for all the nodes and then try to develop a model can identify the true trajectory created by true particles. In the right side shows an example of all the edge you can connect from one represented event. The gray are the fake edge, the red are the true edge. Our task is to develop an efficient classifier to distinguish red from the gray. Here is the Kaggle project for this data. You are highly encouraged to study in detail. They can inspire you to develop an efficient edge classifier to solve this problem. This is an interesting problem that requires relatively large computing facility. If you decide to work on this project, please contact TA. We will try to provide you alternative computing resource in order to accomplish this project. The next project is a digest generative model. This is the same dataset we have used to learn the generative adversary network. In this project, we explore LHC Olympic 2020 Challenge dataset. The dataset is composed of two types of the data. One is the beyond centimeter signal. There's a W prime particle, pretty heavy, 3.5 TeV, can decay to two new particles, X and Y. X is 500 GeV mass, Y is 100 GeV mass. Each of the particle can further decay to quark-antiquark pair, and quark-antiquark pair eventually will initiate showers. When X and Y decay from such a heavy particle, they will be highly boosted. Therefore, the final shower particles will be highly collimated. We can run a jet clustering algorithm. Eventually, there are two jets which can represent the force vector and also the kinematics information initiated from the W prime. Left side is one example. There are two jets, each are clustered, and they are initiated from this new particle. We provide a data set already finished the clustering. Our job is try to classify such signal events from the background events. What could be the background events? In quantum chromodynamics, there's huge number of the quark-antiquark pair production just from the proton collisions, and each can also initiate the jet. The question here is, can we identify such a signal event from a background event? The jet algorithm used for this study is based on anti-KT clustering algorithm using FatJet package with jet radius 1.0. There's already a pre-selection kinematics applied to the jet. Each jet requires the transverse momentum greater than 1.2 TeV, and the rapidity should be less than 2.5. For each event, once you get two jets, you can calculate the invariant mass of two jets. The QCD background expect to behave as this falling spectrum, while the BSM signal expect to have a peak structure around the new physics invariant mass point. MJJ would be one of the most efficient observable to do such a signal background classification. However, to carry out such a study, we will need several technologies, including the fast detector simulation. The key approach of paleophysics is to generate Monte Carlo simulation with a sufficient statistics and compare with the data collected from the LHC. Through this study, we can fine-tune our Monte Carlo simulation even based on the first principle or from the detector simulation until we can describe the data. This is a quite heavy computing required effort. Generative models can be applied to speed up the full process and then make the discovery early. In the class, we have a practice the generative adversarial network model. For the final lab project, we can try to explore different type of the generative models, in particular variational autoencoders. The data structure is the same as we prepared in the previous course exercise. Here are references of the different approach of generative models. You are highly encouraged to explore some of them. Try to carry out to finish that for your final project. The next data set we would like to introduce is the top jet. Top quark can decay to W boson and B jet, and W boson can further decay to UD bar or CS bar. For a highly boosted top quark, the 3 quark will be collimated and initiate a high multiplicity jet. Here's one event display showing a top quark candidate shower too many hadrons. The early part is the charged particle trajectory, and the tile here represent the calorimeter heat and energy measurement. For this dataset, we provide all the constituents which can be used to build the form vector of the jet. We also provide different type of the jets. There's a light quark jet, U quark, down quark, or strange quark composition. There's a gluon initiated jet, and the W boson or Z boson jet, where W boson Z boson decay to 2 quark in the final state, and top jet have a 3 subjet topology. We can use the constituents of the jet to calculate observables, which might carry useful information to distinguish different types of jets. For example, the mass of the jet, top quark is heavy. You can see the peak at 175 GeV. For W and Z jet, their mass of the jets is around 80 GeV or 91 GeV, while the light jet, the mass is quite small. In addition to the jet mass, we can also calculate energy correlation variables and the other jet shape variable, or even just count number of the constituents contained inside the jet. With this high-level feature, we can use to build classifier, distinguish different type of the jets. We can also use the jet image ideas. Jet image can be built from pixelated version of the jet constituents in two-dimensional eta-phi plane. Through the jet images built from the constitution of jet, we can develop deep convolutional neural network model to classify different type of the jet. We can also use the jet constituents as input directly to build recurrent neural network style of the model to do classification of the jet. Here is a set of references for scientists to build different type of the deep learning model to attack the same jet physics problem. This can give you quite inspiration about the model for your project. The final data set is the electron shower data set with the emerging detector. This is an alternative data set, very similar to what we have done in the energy regression class, but with more realistic setup. Let me introduce the emerging detector in detail. This is the design of the emerging detector in the phase experiment. Here is a emerging detector box. A cartoon of this emerging detector box is like this. There are 770 layers of an emergent film and 1 mm tungsten plate. The cross-section of the emergent film is 25 cm by 30 cm. The full length is 1.1 meter. Because 770 layers of the 1 mm tungsten plate, it weighs 1.1 tons, about 220 radiation length. Let's zoom in just a part of the emergent film. Each emergent film is composed of 2 emergent layers. Each is a 50 micrometer, and sandwich between is a plastic base, about 200 micrometer. If you zoom in the emergent layer, it's composed of these 0.2 micrometer particles. It can provide high precision measurement of the charged particle trajectory. In order to build the track when it travels through the emergent layers, we need to build a base track for each of the emergent film first. The base track is just a short segment combined from 2 microtracks. When you have a charged particle go through each emergent film, it should supposed to deposit 2 hits in emergent layer, and we can try to combine them to build base track. Then we can link base track in order to build a full trajectory of the particles. When an electron comes into the emergent detector, because of the tungsten, it will initiate electron shower. For energetic electrons, there are more number of the shower particles will be initiated. Here's just one comparison between a 100 GeV electron from a 1 TeV electron. If you look at cross-section view of the electron, and we can count the number of the tracks of each plate. The shower profile along the longitudinal plane, there will be a maximum happen, and then the number of the track will be reduced. So we can either just count total number of the track deposited in the emergent detector for the energy regression. We can also use the peak position of the shower maximum and also the number of the particles at the shower maximum to do the regression. Even more advanced, we can use the number of tracks per layer to build a deep learning model to learn the shower profile in order to further improve the energy resolution. But there's a complexity. The electron is actually embedded with a large number of the muons. Muon can travel through the full detector without initial large shower. In the actual data, the electron shower will be embedded with a huge flux of the muons. In this dataset, we provide the cluster of the muons. You can study the difference of the muon cluster from the electron cluster. Once you have the electron cluster, you can go ahead to build the regression model similar to what we studied before. But instead of just using the total number of cluster-based tracks, you can try to develop more advanced model. When you derive the regression energy, you can categorize your regression model in terms of the bias and also the resolution as a function of the truth energy. Alright, this is a link to the data set. Here are references you can study which contain more background knowledge to the detector and explanation about the working principle behind the electron shower regression.